All right, cool. All right, welcome back. Um, Hi. Good to see you guys. Um, so today we're gonna go. We started last week. We started Divide and Conquer. It's actually really great because the other groups did not get to Divide and Conquer. With the Israeli groups, only got finished recursion, so you guys are a little bit ahead. So we only have to finish this PowerPoint today, and then hopefully we'll finish early. Uh, but yeah, this is one of my favorite uh, presentations. Like what?
What's with the picture? It's
Oh, I explained last time.
yeah,
It is here. Yeah, Philip II of Macedon, who's the father of Alexander the Great, who coined divide and conquer. Who like that? They attribute that he started. He said that first. I saw the picture also in the material. I was like, why did they put a picture of a statue? So I looked it up on Google. Yeah. Anyways, okay, so we did this last time. Divide and conquer is a paradigm. What is a paradigm in algorithms? It's a particular method that we use to solve a certain problem. So it's an approach to solving algorithmic problems. Now we're going to see in this course, we're going to see divide and conquer in this recitation. There's dynamic programming. We're going to see it later on. We're actually going to see an example of it today. And greedy algorithms, we're also going to learn this at the end of the course also. So these are all paradigms. There are approaches that it's the same exact type of answer, but for different problems. Okay, so this is a reminder from the lecture. Divide and conquer. We divide up our problem into smaller problems. We solve each one of those smaller problems separately, and then we combine them back up. All this happens recursively, not necessarily in this order, but let's say sorting. This is merge sort, right? You learned it in the lecture. You take the array, you divide it into two, and you keep on dividing it into two until you get to one element, and then you sort it as you go back up. You sort the two halves of the array as you go back up. So that is merge sort. And now an example of this is a good example of what we have is divide, solve, and then divide, and then we merge it. So divide and then what were the three things? Divide, solve, and combine, right? So in merge sort, what do? We first divide, and then we combine each solution, and only afterwards we solve, right? So it's not necessarily in this order. When we just solving the heavy lifting, when we divide the array to two, we call each one recursively, and when we add them back, what do we have to do? We have to compare both elements. We have to combine two arrays into one longer array, right?
In this case, in merge sort, it is in this order. It's just
it's not in this order. These are
no, because you repeat them. You divide all of them, and then you solve, and then you combine, and then you solve, and then you combine, and then you solve.
Exactly. But the heavy where all the complexity happens is here. This is O of n to combine both smaller arrays. That's why it's like not exactly in this order. But then for quick sort, what do? Did you learn quick sort in the lecture?
Not exactly.
Not exactly. Okay, so quick sort is something similar. What we do is we choose. I can't get into that. They're going to learn it in a lecture, in a future lecture. It's just a general idea. You choose a random element, let's say 5, and you choose that as your pivot. What does that mean? You're going to go through all these elements, right? And you're going to say you're dividing into two groups. One is smaller than 5. The other one is bigger than 5. Okay, and then you operate recursively on each of those halves to sort them. So here we're what?
We talked about something similar, but it was
okay. Yeah. Amazing. So here, what happens? All the heavy lifting, the big complexity happens at this stage before we divide, right? Because we divide it into, let's say here there's like 2, 4, 3, and here there's 12, 9, 7, right? They're not ordered. But the second we divide them into two groups, that took us O of n, and the second they come back sorted, we don't have to do anything, right? The second it comes back from the recursion sorted, it will be 2, 3, 4, 5, and then 7, 9, 12. It'll come back already sorted. So the heavy lifting was done before we divide. Is that understood? So it's not necessarily in the order we saw before. That's my only point here. Okay. Binary search, I'm just going to go over it quickly. Even though we kind of did it last time, it's where each time if you have a sorted array, let's say if our array was 2, 4, 7, 12, 15. What you do is each time if you're searching for a number, say I'm searching for 12. So you look at the middle element, you compare it. If it's bigger than this 7, we know it's in this half of the array. If it's smaller, we know it's in this half. If it's equal, we found it. So we operate recursively, and then we take the half here. Let's say the half is actually, we take the lower half, you'd find 12 and you'd be done. So searching in a sorted array actually is very quick. It's recursive, it's O of log of n. So here, this is basically what I said. What I said on the board. All right. So how do you binary search? Okay. And how do you implement this? Obviously, recursively. Okay. All right. So this is an example we did last time. I'm not going to go over it again. But first, you guys remember how to solve this? Because we did this last time. So you should be able to remember a little bit. If you have an array where it rises and falls, and we will find the point where it's the top of that rising and fall. So what did we do?
We need to check the left one and the right one.
Of which element?
Middle.
The middle, exactly. Like binary search, we look at the middle, we divide it into two halves. So we look at the middle, and we look at its two neighbors, like you said, and we check if they're both lower than it. If they're both lower than it, we're done. If not, what do we do?
To the size, the bigger.
The bigger side?
If the left size is bigger, we go there.
We go to the smaller side. Why do we go? Oh yeah, wait, you're right. We go to the bigger side. I got confused with the other one. You're right. We go to the bigger side because then we find it.
Yeah.
Okay, my bad. All right. So that's what we do. I'm not going to go over all the writing of the code. This is a pseudocode. The runtime, we divide it into two halves every time. So this is the recursive. You have to be able to build the recursive formula. And the recursive formula we did last time, how to solve it. But this is just master theorem, which is O of log of n. All right, this is the second one we did last time. Okay, so we need to find where water is basically raining on these buildings. We need to find some sort of building where its two neighbors are taller than it. Now there could be many of these, so we just need to find one. So how do we solve this one? This is why I got confused last time. How do we solve this one? Do you guys remember?
Start from the beginning. Or also from the beginning.
So from the middle. To start from the beginning would be O of n. Right, you just go. Right, that's the naive. The naive is from the beginning. What?
So
what do we do?
separate it for two parts.
Yeah, we check the middle one, separate into two halves. But how do you check for if you got the correct element and then which side do you
Need to.
then say we check the middle one, right? Here it's this one. Now what do?
Remember that
We check
We go to the.
We go to the smaller one, exactly.
Smile.
Yeah, we go to the lower one, but even before that, we have to check if maybe this is our correct answer. We check that its two neighbors are higher than him. If not, then we go to the lower half of the array, and we're promised because of that we check that this one is higher and this one is lower, so we're promised that there's one somewhere here.
Check the neighbor that we came from
Exactly.
because he's lower than.
Exactly, because he's higher than his neighbor, so we don't have to check him. Yeah. All right. So that was that answer. No. And now we're going to skip to, also this is O of log n. We just divided into two halves again. We're going to go to the next question. Okay. All right. So what?
Nothing.
All right, input is an array of n distinct numbers, like there is on a board. Technically, if it's distinct numbers, I don't know why it's 1 and 1, but it doesn't really, I don't think it matters too much. We need to find a subarray from some point to some point, that the sum of all of those elements is the maximum possible value. There could be multiple of them, and that's why you're laughing because you did a question like this.
I'm laughing because I'm pretty sure that Artyom explained this for the club like a year ago.
Really?
Yeah.
That's so funny. All right, you want to teach?
Oh.
Okay, so like I was saying, there may be more than one maximum sum subarray. So we must say that it is a subarray, right? There could be multiple. We just need to find one. We don't need to find all of them. We don't need to find the maximal, right? Or the maximum is the biggest. There can't be anyone with him. So we want to find the greatest possible one. Well, there could be others. So anyone have any ideas? Right here we have 3 and 5, and also 8 is maximum.
I don't remember exactly.
Artem can tell. You can't answer.
Bro, so.
What?
That makes sense.
But how would you do that? You're right. We're divide and conquer. We want to divide it, split in the middle.
And
Okay.
I remember correctly, your result was without it was linear. Yeah.
It was what?
Linear.
Okay.
So yeah, what it is linear. But I remember he did was just go over you need an auxiliary array, so that it has a auxiliary size of n, and you go over everyone and you sum it to the previous. It's a cumulative array, so you sum the previous.
Oh yeah.
And when you are negative, you set it to 0 because every time you're negative, the total amount is less, right?
If you have a negative prefix, it like puts you down, so you always want to drop it.
To 0 though, or you just drop it the amount?
You drop it. You drop like every time, like you go, and you sum elements one by one, and every time on every iteration you update your answer. And the moment your total sum becomes negative,
then you reset it.
Yeah, you reset it.
Got it. So it's not when you get to negative number here; it's when the sum becomes negative. Okay. All right. Cool. All right. That's definitely probably a valid solution. I trust you. It's probably a valid solution. Here we're doing divide and conquer. So how would we solve this?
You would sort it first, and then you would.
No, sorting is in login. Why would I do that? Okay. So note that one of the following is correct. There is a very heavy subarray in the first half, in the second half, or both. What does that mean? Let's say we divide it into 2. Right? So we know that the heaviest subarray is either wholly contained in here, or it's some sort of start from here and some sort of end of this one and some sort of start of this one. Suffix and a prefix. Those are the 3 options. Okay? So what are we going to do? We'll find the heaviest one contained in the first one, heaviest one in the second one, and heaviest one that starts here and ends here. And we'll compare those 3, and then we'll return the largest one. All right. And then obviously the heaviest one here and the heaviest one here, both are found recursively. So let's do an example. I don't know what animation is. Okay, here. Find the heaviest part of the right subarray. So the heaviest part in here, right? Oh wait, sorry. I think what was before is you just sum over everything. Here we just sum over it. Okay, so never mind. So here we're just trying to solve we're just trying to solve the ones that start here, like that start here and end here. That's the only one we're trying to solve. So we'll find the heaviest part of the right subarray. Add the sums. Sorry, maybe I should just expand on the board. 1 second. Okay, so it's not explaining here how to find in here and in here, but we just find it recursively, right? We just find it recursively, and we'll get from the recursion, we'll get the heaviest one within here and the heaviest one within here. Now let's say we have the answer from here and here. How do we then produce the final answer?
We have to return this heaviest prefix and heaviest suffix for every call, recursion call. And we can recalculate it in O1, like using a reverse formula.
I didn't get what you were saying.
Okay, so should I say it again?
Yeah.
So it's a recursive thing, right?
Yeah.
So with every recursion call should return for us the heaviest subarray, also the heaviest suffix and the heaviest prefix.
You're right, but you're right. Well, you're right, but that's the second answer. We're doing the first answer here. More naive. Okay. That's what you meant. No. That's where we're gonna go with this. But first, we get the heaviest subarray from the recursive call. So this is heaviest. Let's call this L, and this is R. So this is heaviest L, and this is heaviest R, right? So we know what the heaviest one here and the heaviest one here is. Now, how do we turn the heaviest one in the whole array? We have to compare this one to this one, and then also somehow we have to find the heaviest one that starts from here and ends in the second half. Okay, so the first one is very easy to calculate. It's just from the recursion. We just get it from that. But now how do we get the heaviest one that starts from one and ends in the other one? So here. So basically, you note that if it starts here and ends here, it's a suffix of this one, right? It's the ending of this array. It has to go until the end. We can start whenever we want, but we have to go until the end. And here we can go until wherever we want, but it has to start from the middle, from the beginning of the second subarray. So it has to start from the middle there, but it also has to end in the middle on this half. That's why that animation is really confusing. All right. So. So we'll add the Sorry, give me a second. I just don't want to say anything wrong.
I think we start from the ruler. We go back. If the number is minus, we need to continue. And if the first number is minus, we need to continue left. And then we get a positive number. And then we have also we get a positive number, and then we get negative number. So we stop.
Okay.
This is the sum.
I think
yeah. And in the right side, we start from
the middle.
A positive number. So if we continue and we get the positive number, we will continue. And if we get a negative number, we stop. So
okay, but it could be that once you get to a negative, like -2 here, you want to continue.
No.
You're saying if the sum becomes negative?
No.
No,
They don't continue.
So
you're saying that we start from the middle and we start summing?
Yes.
The second we get to negative, we stop?
This is what they do.
This is
No,
no, it's confused just.
Yeah.
I,
Yeah.
you want to know how do we recalculate?
Yeah.
So like it's in O1 because like you want for this whole array, you want to calculate for the heaviest suffix, right?
Yeah, they have a suffix.
So you take max of the suffix of this part,
Okay.
and the whole.
No, but you're just going to the next solution. You're going to where you just
No,
to return
no, you can
prefix.
calculate the
How do you calculate it?
sum of the subarray in O1 if you pre-calculate the every prefix of every.
Okay.
You see what I
I see what
mean?
you're doing. Yeah. Okay.
So I think
that's not.
I think what he's
Or
trying
you can
to
just return the sum of the whole of it. So you're gonna return like 4 parts. The heaviest subarray, the sum of all subarray, the
Yeah, that's what we're gonna do in the next one. I'm just confused because here we're not. Here's like the naive way. It's like even before it'll become like n log n.
I think it's trying to find
This one is n log n. It's more naive.
I think it's trying to find like the heaviest and also like the heaviest one to the right kind of thing.
Exactly. I think it's like what you said. It's some of the trick where you start from the middle and you just find the largest. You just sum each one, right? You just take, if we start at -6 plus 5. So here you have -6 sum, here you have -1 sum, here you have 2 sums. You just sum it. And then you return the max one that you get. So it's really O of n processing to get the largest prefix and the largest suffix.
for every recursive call that's all.
Exactly. For every recursive call, it's O of n. Very inefficient. Sorry that took me so long. But yeah, you had it. You do the sum. That's what you meant, right? Okay. All right. So then the running time is 2. We're divided by 2 every time, splitting the array in half, plus O of n. Therefore, by master, it's n log n. Now that's really bad solution because you can just sort thing or, well, actually here you don't sort, but like it's really bad. So we want to improve it a little bit, and that's what Artem was saying. That if you already know what the heaviest prefix is and the heaviest suffix of every recursive call, I can just take those, right? And then it's O of 1 because I already know the heaviest prefix and the heaviest suffix for this one. You just add them together. Addition is O of 1. So what are we gonna do? Okay, so we're gonna focus on the right half, right? Okay, so we're gonna divide this into half. Both halves that are coming from the recursive call. We have x and y. They come from the recursive call. Each prefix is either each prefix of the whole thing is either a prefix of x, or it's all of x and y and a prefix of y. Right? We can't have half of x and prefix of y. It has to be either all of x and some of y, or just the beginning of x. So here's like an example for a prefix of x, or you can have all of x plus a little bit of a prefix. So what we're going to do, we're going to expand our recursive calls a little bit, like I said, that we're going to also return the weight of, like we already returned the weight of the entire thing, but now we're also going to return the weight of the heaviest prefix and the weight of the heaviest suffix, right? And that we can do in a fixed amount of time, like a constant amount of time. So for a very large array, the weight of the array is the sum of the weights of its 2 halves, right? Okay, and the weight of the heaviest prefix is the maximum between the heaviest component, right? Because we got, let's say this is our array. We divide it into half. This is from the recursive call. We know the heaviest prefix from here. We know the heaviest suffix from here. Same thing here, right? So either it's the heaviest prefix from here. Sorry, the heaviest suffix from here, plus the heaviest prefix from here. Sorry, let's say we're calculating the prefix, right? So we need it to start from here. So either we take the whole sum plus some sort of prefix from the second half, which we'll get from the recursive call, or it's just the heaviest prefix of this recursive call. So we return the maximum of those two, which is basically just O of 1. Same thing for the suffix. If we want the suffix of this whole thing, what we do is we just take either the heavy suffix of this half or all of this plus the heavy suffix of that half. And that's all happens in O of 1. Any questions about this? Because I got kind of confused. So if anyone's confused, please tell me and I'll go over it again. Okay, so I'm going to continue. All right. And then obviously the other half is symmetrical. It's the same exact thing. So therefore, like we said, the local processing is done in O of 1, right? This whole prefix calculation, suffix calculation, whole sum, and also the heaviest in the whole thing. It's all O of 1 because we get it from the recursive call. And then the total processing time is, now it's the same thing. We divide into half, but now it's O of 1 at each stage, and therefore it's O of n, which I'm assuming that was also your solution. It was O of n, right?
Yeah.
Your one with the auxiliary. All right. All right. Questions on this before I continue? No, all right. Raising to a power. Okay, so the input are two numbers, a rational number and a natural number. And we want the number a raised to the power of n. How do we do this? Any ideas?
Linear algebra.
Great answer. How do we do it efficiently?
I just tries to divide and conquer. That's it.
Yeah, that's a great solution. Why don't we do? Uh-oh. 2 through 40.
Same.
Sammy's not feeling well, he told me.
We're I think it's up.
I got it. I got it. I got it.
What did you?
I got it. I got it.
What's the blue thing?
The blue thing I didn't use in the end. It's the USB thing. Some classes you need the USB. Here you don't need it.
Oh.
All right. Okay. So we need the number a to the power of n. How are we going to divide and conquer?
Nice inside. Yeah.
So we can divide this into a to the power of n divided by 2 times n, a to the power of n divided by 2, right? So first, naive is just do the multiplication, n times, that's O of n. But let's do it a little bit better. Okay, as we know, like I said, a of n equals a of n divided by 2 to the power of 2. So we can just define a simple function that raises a to the power of n, where it just does the half, it splits it into 2 halves, then it times between them. The times is O of 1, right? So the runtime is just t of n equals t of n divided by 2 plus O of 1 is log n time. Now what's the issue here? Exactly. Our issue is it doesn't handle odds, right? Because we said n is a natural number. So our recursive call is not, the output is not, it's not an input for the same problem, right? Because if it's odd, n is already not natural. That's already an integer, right? Not an integer, it's a rational number, right? If we have a to the power of, let's say, even bigger number of, let's say 13, a to the power of 6.5 times a to the power of 6.5. It's not we can't recursively call that because it's not the same problem that we started with. So how are we going to solve this?
-1.
We're going to divide it by a to such that we get to whatever power of 2 is the closest, and then we're going to.
Yeah, kind of. We want to get to an even number, right? So first let's do this. It's a bad solution, but let's do this. We will do n divided by, if it's odd, we'll do n divided by 2 but -1, and here it's +1. Right? So we solved our even odd case, but what's the issue here? is that the runtime is really bad. Because now we have two separate numbers we need to calculate, right? The whole point was that we need to divide it into two of the same number, and then we save runtime. But here, the worst case is that we do a bunch of odds. So instead of being t of n equals t of n divided by 2, now it's t of n equals 2 times t of n divided by 2, because we have to do two recursive calls, which is not good. So how are we going to fix this issue? We kind of said it a little bit. You said it, Thomas?
You get to whatever, like you divide by a, and then that's and then multiply by whatever.
Yeah, basically, we're going to take away one of the a's, right? We're going to take away one of the a's, and then we have two of the same number. And here, it's actually a much better recursive formula, because we're calling it, again, only on the number divided by 2. And it's the same number, so now it's only 1 times t of n divided by 2. So the runtime would be, now it's O log n, much, much better. It's definitely fastest you can do.
Did you make this, depending on if you made this or you only translated my comment?
I translated it, go ahead.
This is bullshit, you know, right? Because
yeah. Ready? I might be saying what you're about to say.
Sure.
Okay, so there's a little bit of an issue with that. What's our issue? That there's the amount of operations we do, and then there's runtime, right? Numbers take up space on a computer. If we want to represent a number, it takes log of that number, bits. Now, for example, if we want to calculate 2 to the power of n, how many bits do we need to represent that number? We need n bits, right? So in order to write n bits, I have to write n bits. And therefore, I need n operations to write those bits. Does that make sense? So therefore, it's not possible to do O of log n, because we need at least omega of n, because we need to write those n bits.
Yes.
Does that make sense? So there's an issue, right?
Yes.
So not exactly. Okay, in a computer, in this course and in general, it's assumed that a word is theta of log n. Why? Because we want to be able to represent an array of n. So we need to be able to access that with the index, right? So the index has to be at least of size log n to access the array. Otherwise, you won't be able to access the second half of it, unless you do tricks. But so therefore, memory cell is theta of log n. Okay, the processor is capable of performing. We can do processing on a whole word in log of n bits. So on log n, not in O of log n, it's O of 1. We can do O of log n bits, correct? So therefore, we can actually, in reality, hope for a runtime of n divided by log n, because we can write, instead of the n bits 1 by 1, we can write the n bits log n bits at a time. The computer can do all that in O of 1. But we can't get any better than that. In the algorithm we described, the multiplication will not cost O of 1, and that's why there's the error in that analysis that we had before. Okay, but that's not completely, that was completely correct, but now we're going to change the problem a little bit, and it'll fix everything. If we instead, basically, there's a difference between the number of operations we do and the runtime. Okay, the number of operations is still theta of log n, like that's the amount of operations we did. But the issue with the runtime is it depends on the size of the input and output. So if we want to fix our problem to actually get multiplication, like to the power in O of log n, what we do is we can take the field of a specific prime number and then calculate the power, but mod that prime number. And if we do that, we bound the number, hopefully by smaller than the amount of a word, right? And if it's smaller amount of a word, we can write that in O of 1, and we can get theta of log n.
Only if we return the mod result.
Exactly. Only if the issue, the problem is that we need to return mod of the result. Yeah. To like something to the power of something mod a prime number, then it's bound by less than O of log n. By the log n bits.
If p is not prime.
If it's not prime, it's not. Then it's not a field.
Yeah, but it still works. So.
Can
It still works. I'm not sure.
Can you go back 1 sec?
Yeah, to the previous one.
Yeah. What are we trying to do?
Basically showed that it was O of log n, right?
Okay.
But then there's an issue with that because we still have to write those n bits on the computer.
Yeah.
So.
I mean, I was trying to say that calculating bigger numbers is harder.
Okay.
So if you're multiplying a by a to the 12 and multiplying a to the 6 by a to the 6, it's like the same.
You're saying that if a to the power is like a to the 6th power and a to the 12th power is like the same?
No, if you're multiplying a by a to the 12 or a by a to the 6 times a to the 6, I don't think there's much of a difference, but I'm not sure.
Maybe it depends. I think there is a difference. Also, it's a theoretical difference because, right, and technically all the overhead from the recursive calls will be a lot more than just simple multiplication. Because really good at simple multiplication.
Yeah,
I think technically if you did both solutions in IDE and you checked the runtime on a really big number, regular multiplication might be faster.
Depends how big
the number
exponential is.
Yeah, but you can definitely test it out and see from what number is already faster. Okay, any questions on that really complicated? I hope I explained it well. Everyone understood that? So any questions? All right, now we're gonna do another fun question. Actually, really do like these questions. It's definitely algorithms are more of the fun part of the course. A lot more than the math and the data structures. But all right, so we need an input. So our problem is an input. We get a natural number. Output the Fibonacci number of order n. Okay, so already it kind of shows you the naive answer. The naive is just basically just use the definition, calculate it, right? It's a recursive formula with O of 2 to the power n, which is really, really bad. Exponential is really bad. But we need to find something better than that. So anyone have any ideas?
Use the golden ratio.
Just the what?
Golden ratio.
The golden ratio. Okay, that I'm not sure.
Yeah, that's how I do it. Actually, just you have a number and you multiply it by some whatever, and you get the.
If you multiply the golden ratio by.
No. What we should just put it on your computer 1 second is
no, it's okay.
Finding a number using the golden ratio.
Okay, we'll go into that afterwards, maybe. But we're gonna do something a little bit more divide and conquer. That basically we have our number f of n, right? Which is basically equal to we have a recursive call on f of n minus 1 and f of n minus 2. Now what is this one? It's basically f of n minus 2 and f of n minus 3. And this one is also f of n minus 3 and f of n minus 4. And if we keep on going, we get f of n minus 3, f of n minus 4, so on and so forth. Now you can see I calculated f of n minus 2, calculated it twice. It's really inefficient. And then f of n minus 3, I actually calculated 3 separate times. F of 4, I'm going to calculate more and more and more times. This tree just gets exponentially bigger, and we're doing a lot of very redundant calculations. So how can we make this a little bit better?
Minimalization.
Yep. So that's actually, I think that's the answer that we do here. Yep, exactly. We do memorization. What is memorization? We'll learn it in dynamic programming. We're going to have 2 recitations on that and 2 lectures. But just the basic idea of dynamic programming is let's use memory. Instead of trying to calculate everything without using any additional memory, let's just use an array or a 2D array. And let's just calculate all these recursive calls so we don't have to do them over and over and over again. So what are we going to do in this one? We're going to take an array of size n, the one that we want to calculate. And we start from, our base case is the Fibonacci number 0 and 1, or just 1 and 1, right? And for each new cell, what we're going to do is we're going to go through the whole array, and each time we're just going to calculate this one be the sum of the past two, the one before it and the one before it, right? So then the sum here would be 2, and then the sum here we just sum these two, 3, and then 5, then 8, so we get to whatever the n number is, and then you can tell it's O of n. Instead of 2 to the power of n, we just saved all those really redundant recursive calls. Instead, we turn this idea and we use memory to then just save the calculation so we don't have to do them again. Okay, so that's dynamic programming. We're going to learn it a lot more in depth. That's the general idea that we can do it in O of n. All right? Cool. Now we're going to find, like Thomas said earlier, a linear algebra solution. We're going to use matrices.
Oh, we can put it in the power.
Yeah, exactly. Exactly. All right, so if you take the vector representation of Fn and Fn plus 1, this isn't, I think this is a bit off because it should be Fn plus 2 equals the sum of those two. Anyways, you take the representation of Fn plus 2, the vector representation, and you take the same representation of the number before it, and you times it by this matrix. What do you get?
Next.
What?
The next.
The next one, exactly. We can do it quickly. This times this. You have Fn plus Fn minus 1 equals just Fn plus 1, right, by the definition. And here, you just get F of n. Okay? All right, good. So now let's open up one. What? Use, what do you mean? Do we use this like the solution?
I knew it. There was a
You missed it. I said Thomas called it. Do we use like this solution?
It's before the Fibonacci.
What do you mean? Like,
I
oh,
know.
do you mean in real life? Like in
No, in the matrix I didn't saw it.
what do you mean? Pagin.
שבחיים לא ראיתי כאילו שימוש במטריצות האלה, כאילו בדרך פתרון הזו.
הבנתי. אז כן, משתמשים בזה במבחנים וכאלה. כן, צריך להכיר. It is a trick. I think I saw a test question that like just took this and just made it harder. So you do have to know it. Okay, so let's open up one level. So therefore, this equals just this is just the previous number times the same matrix. So now we have this matrix times itself times the number. So that's basically just this matrix to the second power, right?
Nice.
All right. And so let's do that a bunch of times. What happens if we do it I times? We get this formula. Fn plus 1 and Fn, the vector of them two, is basically the same matrix to the power of I, of Fn plus 1 minus I, and Fn minus I. Okay, so technically you have to prove this statement because we don't know if it's true. I mean, it's cool, that's like the seeing a couple examples. Just like we did in the substitution method, you have to prove it. Sorry, the iteration method, you have to prove it. I'm not going to prove it. So what can we do with this now? Now that we substituted instead of I, we can do n equals to this to the power of n times 1 and 0. So now what can we do?
Solve in log n time.
Yeah, we can use the same algorithm we did before for the raising a to the power of n. We can use that here, right? Because before we had a to the power of n, now we just have a matrix to the power of n. We can use that same algorithm, calculate this in log n time, the matrix to the power of n. So reminder, the power problem, we can see that this can be solved with log n multiples of n. If A is our matrix, multiplying two matrices of 2 by 2 is constant time. So therefore, it'll take us log n constant operations using the same logic as before. And therefore, we can do this. We can solve it in log n times exactly, calculating the nth Fibonacci number. All right. Last problem for today, and then we're going to be done really early. It's not great.
Yes.
Everyone wants to go home. Not first time ever. The first one, I think we finished earlier. The second one of them we finished earlier. All right. So tiling problem. We have these R-shaped tiles, right? Basically an L or an R, three tiles in that shape. They're given a board of n times n such that n equals some sort of power of 2. And we're given one burnt tile that we don't have to cover, otherwise it's not possible. But if we have one tile that we don't have to cover, show that the entire board, besides for that one tile, besides for that one tile, can be covered using those shapes. It's kind of, this might remind you of in discrete mathematics, you learn you prove something similar in induction. Right, I think you might have even proved this with induction.
Yeah, probably.
But you do something very similar. So how are we going to show this? What's our algorithm this time?
That's very.
It was similar?
Yeah, it was I think the candy bar one. So like
Oh yeah. Yeah, the candy bar one. Yeah, that's from there.
So divide by k.
Well, what?
Divide the corner divide by k. Right?
We divided by k?
Like we divide dk to k divided by 2, and then we can unite those. Like we divided from before.
Into yes, there you go. We divide into 4 and then what?
Yeah, and then
In the middle.
we for each and every one. We consider the one with the burnt square as a standalone case.
Okay.
All the others is obvious. Because we can do them ways of this.
No, it's not.
No, it's not. So let's show that we can fill them all except like for the center 3. So we're gonna need here.
Exactly.
Right.
Exactly.
And then also another.
Wait, that's the thing? Okay. So, like you said, we're gonna divide into 4 parts. And we're gonna put the R-shaped thing on the 3 quarters that don't have the burnt spot. So now everyone has one burnt spot, right? So we'll divide it into half. And then what we'll do is we'll put our R on the 3 quarters that don't have the burnt spot.
And
Now
then
each one of them, exactly. Now each one of them has one burnt spot. So we can solve it recursively. Cut these into quarters. And then put our R-shaped tiles on each one. Like so. So now each one of the
again.
16ths has one burnt tile. And then we do it again. And now you can see that it's a 2 by 2, and each one has one burnt spot. So we just fill it in with our R's, and we're done. All right, cool. Okay, what's the complexity of this one? Thought there was complexity.
All of
Log k.
no
We have. Do it slowly.
A over.
What? Maybe they didn't put it in there because it's kind of complicated, but we have n squared tiles, right? guess it's a bit different because it's tiles and not numbers.
It's they don't need to do anything, just need to show. It's not allowed.
Yeah, you're right. But technically, the runtime of the algorithm, we divide it into 4 every time.
Or divide by 2. We divide k by 2. That's
So it's log 4 of n.
Equals 4 times. Technically, I don't think this is formal at all. Plus, yeah, it's kind of hard to do it because how.
What I was doing. Should I assign a piece to every square or like?
What do you mean?
What's the algorithm doing? Right.
The algorithm is just dividing it into 4 halves and then putting a little r on the 3 quarters that don't have.
No, I got that. I'm just saying that what we did takes log k time because on every iteration we divide the k. The k is the size of the 2k to the power of
To
k.
the power of k, yeah.
Is the size.
Is the size,
every
yeah.
time.
To the power of k times to the power of k, because it's a double array.
Oh, right. So it's k. It's just log. It's just not log. It's just k of k. Because the size goes from 2 to the power of k to the power of k minus 1.
Exactly.
Right.
Yeah, but that means each time we're also doing O of 1. Which let's assume that we do O of 1, then you'd be right.
Yes. And
If
then
it's O of 1, then we really do it like you said. We can just treat this as 2 to the power of k times 2 to the power of k instead of n. And then each time it really gets smaller by 1. Oh, sorry, this is minus 1.
it's very hard.
What? I think you're right, and it's really O of. Okay. Was it each? Okay, whatever. If anyone wants to do this with me afterwards, you're welcome. But we're done for today. To finish all the questions, I just thought to myself that it would be cool to know this.